Hello. I guess my microphone was muted. I don't know how far did you catch on what I said. I hope you guys are having a good day. Uh, Test number two is fast approaching. I guess it would be next weekend. So I'm thinking maybe next week we can start talking about, or we can have a review for test number two. But I guess Dr. Almus already uploaded the review a review worksheet for test number two as well as the answer key. So perhaps next week or on Friday we can talk about that if you have some questions on that. But the bottom line is I hope you guys have started working on or trying to review for test number two, because I guess the coverage would be um, involves a lot of formulas and so on. Okay, plus some things that you should remember from Cal 2, or sorry, from Cal 1. All right. So let's see. So last time we talked about arc lengths. Do you still guys have questions about arc lengths, or is it fine if we move ahead for surface areas? Because I remember last time we had two or three examples about computing the lengths of arcs.
We could do
So
like two or three more arc length equations. Would be nice.
okay, yeah, good. Do you have any particular problem in mind?
None. Just I'd like to see it a little more.
Okay, yeah, sure, no problem. Well, let's try. I can go freestyle here. Of course, there are some problems in the worksheet that you can select, but one student from my previous class asked about this. So let's see. Oops, let me just cut this one and start a new. So let's have this problem. Find the length of the arc. So I hope you guys are getting used to my handwriting. So here we need to find the length of the arc formed by f of x equals hyperbolic cosine x over the interval 0 to ln 9. Okay. I picked this particular example because this will illustrate how important it is for you to remember some concepts from Cal 1. Okay. So if you recall, the formula for the arc length is just an integral over AB, where A and B are the bounds for which you want to create your arc. The integrand would be the square root of 1 plus the derivative squared dx. And if your function is given in terms of y and the bounds are also given in terms of y, you can set up the integral using y analogously. So you'll have an integral from c to d of the square root of 1 plus g prime of y squared dy. So no big adjustment to that compared to volumes and areas. Okay. So the main ingredient for the formula for the arc length would be f prime. So if we look at f prime here, the given function is hyperbolic cosine. The derivative would be hyperbolic sine, right? And then if we square that, I'll have simply hyperbolic sine squared of x, right? So therefore, the arc length would be an integral from 0 to ln 9, because those are the x values which is covered by the arc, of the square root of 1 plus hyperbolic sine squared of x dx. Unfortunately, this integral is not that simple because you cannot use u substitution to evaluate the values right away. So you need to recall some identities from Cal 1. So note that, or recall that hyperbolic cosine squared x minus hyperbolic sine squared x is equal to 1. So that means hyperbolic cosine squared x is 1 plus hyperbolic sine squared of x, right? So the arc length is the integral from 0 to 9 of the square root of hyperbolic cosine squared x dx. Then we take the square root. This will just be, oh sorry, this is ln 9. 0 to ln 9 of hyperbolic cosine. I'm getting ahead of myself there, but anyway. And then the integral of hyperbolic cosine is hyperbolic sine, evaluated from 0 to ln 9. But at this point, we need to recall how the hyperbolic sines are computed. But remember, hyperbolic sine of x is e to the x minus e to the minus x all over 2. So, because remember, for the fundamental theorem of calculus, we'll need to plug in the upper bound minus plug in the lower bound. So I need to compute the hyperbolic sine of ln 9 and the hyperbolic sine of 0. So hyperbolic sine of 0 is easy. It will just be e to the 0 minus e to the negative 0 all over 2, which is just 0. Hyperbolic sine of ln 9 will require a little bit of work. This would be ln 9 minus e to the negative ln 9 all over 2. But here you see that e is followed by ln. They are inverses of each other. So what will be left in the first term is simply 9. For the second term, though, I cannot apply the property of inverses right away because e is not directly followed by ln. E is followed by a negative sign, then the ln. But I can get rid of that negative sign using loss of logarithm. So the second term is the same as e to the ln of 9 to the negative 1, right? Or e to the ln of 1 over 9. And at this point, e is followed by ln. So they are inverses of each other. So what will be left on the second term would be 1 over 9 all over 2. And this would be 80 over 9 all over 2, or that's going to be 40 over 9. Okay, so therefore the arc length, remember, is hyperbolic sine of ln 9 minus hyperbolic sine of 0. So it would be 40 over 9 minus 0. And this would be one-dimensional units. Okay, because it is simply an arc length. All right. So I just chose this specific example just to drive at the point that you need to remember some of the basic, at least the basic identities coming from Cal 1, because that will aid in evaluating some of these integrals. Okay, but if you were just told to set up the integral, then you're good at this point. But I guess I wrote in the instructions, I wrote find the length of the arc, so I should give a number. So there you go. 40 over 9 units. Okay. All right. Any clarificatory questions on this? Well, the thing is, okay, so if you don't have questions about arc length, I'll proceed with some examples for surface areas, but you will see later that in the setup for the integral that gives us the surface area, you will still need to sort of set up the integrand, or you need to find the integrand for the arc length because they are really connected to each other. So, and let's see why they are closely related to each other. Because I guess I already showed you this diagram last time. Let's just remember this so that even if you don't like memorizing the formula for the surface area, hopefully this explanation will make sense and you can right away derive the formula for the surface area. Okay, so for the surface area, you should be given an arc. So say the arc formed by the function f of x over, say, some interval ab. And then you will be given an axis of revolution. So that axis of revolution could be horizontal, could be vertical, but in general, this is the case. And then the idea here is we rotate the arc with respect to the AOR. So this is different from what we did last time when we rotate a shaded region. So if you rotate the shaded region all throughout about the AOR, you will form a solid with some non-hollow parts inside, right? But if you are just rotating an arc like what we are doing here, what you get is a three-dimensional object, but that is empty inside, right? So basically what happens here is that this gets rotated over here, and you get like like a cylinder or like a vase. I hope you can imagine what happens here. It's like a vase, which is hollow inside. So that's why you can only compute the surface area here. Okay. Now, how to compute the surface area? Well, the surface area is just the amount of material needed to form the lateral face of the solid. Now, in this particular case, that will depend on the length of the arc or the height of the vase, if you are imagining it as a vase. So that height or that length will just be the arc length. So here, this is the formula for the arc length. Okay, or the integrand for the arc length. For the integrand in the arc length, right? And then times some quantity, because surface areas are two-dimensional measurements, right? Well, the basic thing here is that this arc will travel along the circumference of the circle with respect to the axis of revolution. So here you will have 2 pi r, which is the circumference of that circle, where r is the distance between the arc and the AOR. Okay, so you measure how far is a point on the curve from the AOR, and that would be the value of capital R here, which I guess I was again cut off. Do you guys hear me?
Yes.
Yeah, unfortunately, the internet here on campus is a little bit slow, or at least in my office. So let's, yeah, it's now I have 3 bars of signal, so this should be better. So let's look at some examples from the worksheet. Have you guys had time to look at the worksheet, at least to browse through it? Any problem that stood out? Or you haven't had the time to look at it yet? Well, if you don't have any particular problem in mind, then let me pick a random one. Let me try problem 24. So the instruction here would be determine the area of the surface generated by revolving the curve about the x-axis. So first, the curve C is determined by the function root of 4 minus x squared over the interval 0 to 1. Okay, and then the axis of revolution is the x-axis. Okay, so let's look at how the region looks like. So I guess for surface areas, oh, actually, it's still important even for surface areas because we need to look at the radius. How far is the arc from the axis of revolution, right? So if you look at the function f, this is the upper semicircle with center at the origin and radius 2. So that means when x is 0, y is equal to 2. When x is 1, y is equal to root 3. Let's say root 3 is over there. So this is the arc that we are considering. Okay. And then the axis of revolution is the x-axis. Okay. So the surface area is given by the integral. And then let's use the variable x because the function is given in terms of x. So let's not make our lives complicated by solving for x in terms of y. So I'll stick to the variable x. And another advantage of using x is that the interval is given as an interval in the x-axis. So x's go from 0 to 1. So there you go, the bounds. And then remember the formula is 2 pi radius times height. 2 pi radius times length. So that's the integrand. So copy over the 2 pi and then measure the radius. Well, the radius would be how far is a point on the curve from the axis of revolution. But if you notice, upon drawing that length, it is nothing but the length of a vertical strip, right? And again, we measure vertical strips as top function minus the bottom function, right? The top function here is root of 4 minus x squared. The bottom function is y equals 0. That's the equation for the x-axis. So this would be root of 4 minus x squared. So that would be the radius here, 4 minus x squared. And then remember the next term would be, the next factor would be the length of the curve, right? Or the integrand in the formula for the length of the arc. So that means here, I'll have a square root of 1 plus the derivative squared. Now the function is 4 minus x squared to the 1/2. So if I solve for the derivative, I'll get 1/2, 4 minus x squared to the negative 1/2. Then chain rule kicks in, negative 2x. So again, you need to remember how to differentiate properly. So take note when to use the quotient rule. So usually that is what students miss. They remember it well in Cal 1, but there's a chance that they forget it during Cal 2. So make sure you don't forget these things. And then I'll simplify this first. So I'll have negative x over root of 4 minus x squared, all right? And then remember that goes inside the square root quantity squared, right? And so this will be the integral that gives us the surface area. Well, perhaps for this first example, we can do the evaluation of the integral. And then for the rest of the examples, I'll just do the setup and I leave the integration to you guys, okay? So let's see. So this would be integral from 0 to 1 of 2 pi root of 4 minus x squared. Then I'll simplify the radical here. I'll have 1 plus, x. Okay, 1 plus x squared all over 4 minus x squared dx. Then here I'll have integral from 0 to 1 of 2 pi root of 4 minus x squared. I'll simplify the radicand further. It would be 4 minus x squared plus x squared over 4 minus x squared dx. And then I'll apply loss of exponents for the second radical. This would be root of what? Root of 4 over root of 4 minus x squared dx. Okay. And then from 0 to 1, this guy will be canceled by this one. And then root 4 is just 2. And then there's a 2 outside. So that will ultimately be 4 pi dx. And then when we integrate, we get 4 pi x evaluated from 0 to 1. So the surface area is 4 pi square units. All right. Is that fine? Any questions? So for problems like these, we are hoping that the radicals will nicely cancel each other out, or at least you'll have a good identity to work with, because otherwise it might be hard to solve for the integral, because that might require some techniques that some techniques in integration that will just be discussed to you guys probably in chapter 8. So yeah. Right? Any questions? Yeah, Fatuma, I don't want to say for certain for this exam, because the question is whether you will be doing setup or evaluating integrals. But based on past experiences, most of the problems will require just the setup. There would be 1 or 2 questions that you will be required to solve for the integrals, but not all. I think majority will just be set up. And those that are, at least for previous exams, those where integration is required only involve very basic functions. So yeah, because of the time limit, and you are actually not being tested for solving integrals here, but you are tested for setting up the integral that will give us the surface area. But there would be a couple of questions, one or two probably, that will require you to solve the integrals. But again, most of the times those are just simple integrals. All right. Okay. I'm looking at the textbook, and it looks like all the examples for surface areas and actually Pappus's theorem only have the axis of revolution, either the x or the y-axis. Is that correct? Or have you done axis of revolution that are not the coordinate axis? Because the setup might be different for those examples. So, for instance, what if the AOR is a y equals -1? Did you consider examples like this in the lecture? Or the axis of revolution is always the x-axis or the y-axis? Yeah, I'm not sure if that is by design, that you don't see any example on that in the lecture. Though I want to discuss what happens, at least one example, what happens if the AOR is not the coordinate axis, so that you'll have an idea if this, for one reason or the other, appeared in one of your quizzes or homeworks. Oops. So let's try one example. So same curve, but now the axis of revolution is y equals -1. And then for this problem, let's just set up the integral that gives the surface area. I will just be setting it up because I'm not sure if the integral will be easy to evaluate. So, but the point here is just for us to learn how to set up the integral when the axis of revolution is not the coordinate axis, right? So again, this will just be an integral with respect to x, and the bounds would be the starting x and ending x value for the arc. The arc started when x is 0 and ended up when x is equal to 1. So that's still our bounds, regardless of how the axis of revolution, or regardless of how the axis of revolution looks like, right? So here, axis of revolution is y equals -1, but still the bounds would be the bounds for the curve. So the curve started at x equals 0 and ended up at x equals 1. And then we'll have a 2 pi. Remember, we have 2 pi radius times the arc length, okay? And the thing here is that the arc length didn't change because it's the same as the previous region. Or the previous problem, we are simply rotating this curve, nothing changed. So you don't expect any change for capital L. So we'll still have 1 plus x squared over over 4 minus x squared as your value for capital L inside the integral. This is what we got before. But the radius that comes in this problem is different because remember, the radius for the surface area is measured from the axis of revolution towards the arc. And that's how I define capital R. That's the distance between the axis of revolution and the curve, right? But notice that this length is just the length of a vertical strip. And remember, we compute the length of a vertical strip by using our mnemonic top minus bottom, right? The top function is square root of 4 minus x squared. The bottom function is the AOR, and the equation of the AOR is y equals -1. So we have minus -1. So r would be root of 4 minus x squared plus 1. And that goes inside our integral. Don't forget the grouping symbols. And yeah, that would be the integral that gives us the surface area. Now it might be complicated to evaluate this integral. You can split it into two. The second integral will require, I guess, trigonometric substitution. I'm not sure, but I guess that would be the case. And we haven't covered trigonometric substitution yet. So I leave the answer here, and that's why I said I decided that the problem will just ask for the integral that gives us the surface area. All right.
I remember trig substitution.
Oh, you did that in calculus.
Accelerated calc, yeah. I dropped down because I was like, I don't even know what I'm learning anymore. So,
but you will hopefully learn that next chapter. That's part of chapter 8. And yeah, probably for those who know or who have taken previous calculus courses, there would be a lot of integration techniques that will be coming. You'll have trigonometric substitution, algebraic substitution, integration by parts. So what else? Powers of trigonometric functions. So there are a lot of techniques that will be discussed in the next few chapters. So I hope by now you have started reviewing your Calculus 1 notes, memorizing those formulas, or at least remembering the concepts, because in the next few weeks, more formulas, more concepts, more techniques will be discussed. That means more things for you to remember. All right. So, okay, so let's leave it at that. Let's see. Do you want one more example for surface area before moving on to centroids? Maybe let's do problem on. Oh, go ahead, Robert.
I was gonna say yeah.
Yeah. Any particular problem from the worksheet or probably in the quizzes that you have encountered? If nobody will suggest anything, I'll just pick what? I'll pick problem 32, if that's fine, from worksheet 4. What happened to you guys? Because I remember last Monday you are very active on the chat, sending a lot of questions, but now you are a bit more quiet than usual.
Everything is hitting me at one time right now, so I'm just kind of tired of it. I have an essay due today and like other stuff in physics. I have to study out tests. I'm just like, please.
Yeah, a lot of exams. I was thinking probably it's either the topics today are very easy, surface areas, arc lengths, very formula based. But I guess as you are saying on the chat, and as Robert mentioned, some external functions are are kicking in. Too many assignments, right? But I hope you get the concepts for these topics. I'm browsing through again the exercises. They look very straightforward and easy, at least for this topic. I don't know if that's on purpose because you will just be given very simple geometries to work with, or they are setting you up for more difficult problems in the exam. Okay, so let's see. Yeah, problem 32. So here we have the function x equals cosine y. Y is from 0 to pi over 2. And then the AOR is the y-axis. Yeah. So let's get a feel of how the curve looks like, so that we'll have an idea how the surface of revolution will be formed. X here, Y there. And then let's sketch the graph, which would be a little bit awkward because we are given X in terms of Y, X equals cosine Y. So it's just a rotation of the usual cosine curve that we usually see. So here, when Y is 0, cosine would be 1. Or yeah, X equals 1. There we go. So when y is 0, x would be 1. When y is equal to pi over 2, x equals cosine pi over 2. Cosine pi over 2 is 0. So this is y is pi over 2, and then the cosine curve looks like that, right? And then the axis of revolution is the y-axis, right? But remember, the equation of the y-axis is x equals 0, right? So the surface area is an integral, and again, let's take advantage of the fact that the function or the curve is given in terms of the variable y. So here, let's integrate with respect to y. So we need bounds for y, but we already knew that y starts from 0 and ends at pi over 2. Okay. And surface areas always come with a 2 pi. Remember, 2 pi radius length. Okay. Now the radius again is the distance from the axis of revolution towards the curve. And you notice here that capital R is simply the length of a horizontal strip. And remember how we measure horizontal strips? It's going to be right minus left, right? The right function here is the cosine curve. The left function is the y-axis with equation x equals 0. So that means this would be cosine y. Right? So capital R would be cosine y, and that goes inside our integral. And then we need the arc length. The arc length would be square root of 1 plus derivative squared. We know that g of y is equal to cosine y from the problem. Take its derivative with respect to y, we get what? We get negative sine of y, okay? And then we need to square this. We get positive sine squared y. And that goes inside the radical, okay?
Could you sub the 1 plus sine squared y to negative cosine squared y?
Unfortunately not.
Okay.
Because remember the identity that I was initially thinking of as well is the Pythagorean identity, which says sine squared y plus cosine squared y is equal to 1. But here I want a 1 plus. But if I transfer sine to the other side, I will have 1 minus sine squared y. If you put a negative sign in front of the cosine, you'll get sine squared y minus 1. And even if you jumble this identity over and over again, you won't get 1 plus sine squared. So that won't help. Unlike what we had earlier, we had the hyperbolic cosine and the hyperbolic sine. The identity there is a bit different than the Pythagorean identity. That's why we were able to simplify it. I guess U substitution here won't work as well. I guess here you will need trigonometric substitution. You will let tangent x be equal, tangent u equals sine y. But let's stop here because that is a chapter 8 technique. So at least we have set up the integral that gives us the surface area. Okay. Do you foresee any difficulty with this? Again, this is closely related to the arc length, so you need to remember how you set up the integral for the arc length because that comes as a factor inside the integral for the surface area. I guess the main difficulty here is finding capital R, which is the distance from the AOR towards the curve. If your axis of revolution is the x or the y axis, then that will just be either x or y. No biggie about that. Sorry, not that will just be the function. That will be your function. But if the axis of revolution happens to be x equals a or y equals b, then you need to analyze the situation. You do right minus left or top minus bottom, right? Yeah, I guess this is straightforward. So if that's so, maybe we can go ahead and look at centroids. Actually, I heard that you already started with exponential growth and decay in the lecture. So that means you actually finished discussing arcland, surface area, centroids, and Pappus's theorem in the lecture, which is a little bit fast for me. I usually spend a couple of days on centroids or surface areas. And I guess that's the reason why all the examples that you had were just having AORs that are at the coordinate axis. That makes things kind of more convenient or are easier, right? But I guess you see the concept. These are pretty straightforward, right? Except for the integration part, which from time to time you might encounter expressions that are hard to integrate. Ah, you did the surface area last Monday. Oh, okay, I see. Now let's look at centroids. Centroids are basically the center of mass for a region, or this is also the geometric center of a region with constant density. So that means if you have this region, I hope you don't mind me giving you a quick recap of the concepts, even if you have done this in the lecture already. Number one, it always is good to start with a nice conceptual visualization of the methods or the techniques. And number two, if you will be watching the recordings of the meeting, so you get refreshed on what you did in the lecture. Okay. So say you have the region bounded by y equals f of x on top, and at the bottom you have y equals g of x, and then over the interval AB, and then your region R is over here. Okay. Now the centroid is the geometric center. So it is a point x bar comma y bar. So that would be the centroid. So basically you are taking what is the middle x value and the middle y value, but you take into account the weight of those, those x and y values with respect to the region, or you're weighting or you're averaging them, but putting weights with respect to where those positions are located with respect to your plane region. So what I'm trying to say is, okay, you take the average. So basically for the centroid, for the x component of the centroid, you want to take the average all over the area. So you expect to divide something by the area. And then what do you want to take the average of? Remember, in averaging, you take the sum divided by the total number of cases. Now, the total number of cases here in the continuous case would be the area. So that's why we have the area in the denominator. But what do we want to add up? We want to add up the x's, but weighted by the function value with respect to the region. Okay. So the weight here would be, where is that x bar y bar, where is that x value located with respect to the length of the strip? Because for instance, in this particular x value, that corresponds to this long a strip, this long a vertical strip, right? So, but remember the weight of that the length of that vertical strip is f of x minus g of x dx. So basically we integrate all x's times a weight, but that weight is associated by the corresponding length of the vertical strip at that particular x value, then divided by the area. And that's how we get the middle x bar, or the geometric central x bar. Okay. Now, similarly, if we want to get y bar, okay, we again take the average with respect to the area, and then the top would be a continuous sum, so we get an integral. We want to get the central y value weighted by the length of the vertical strips. Okay, but you will notice there's a problem here. If this is my integral, I cannot carry out the integration because I have a variable y in it, and I'm integrating with respect to x. So we need to translate that y in terms of the variable x. But let's keep in mind that what we are looking for is the geometric center. So if this is the particular x value that I'm looking at, what is the middle y value? Or what is the average y value for that particular x? Again, I'm always marrying the concept of the centroid to the geometric center. So if I am at this strip, how can I find the central y value? Any idea? Christina, 1/2 of what? I want to get the middle of that vertical strip, that pink vertical strip there. So it's going to be 1/2 of what? Come on, guys. How do you get the middle? The middle between f and g.
There's like two equations. I don't remember them.
Right. Oh, Fatuma, here I'm looking at the middle y value. Because remember, y bar is the geometric center. So I want the y's to be at the center to begin with. Well, I need to get the center of this vertical strip. So I'll take the average of f and the g values, right? So basically, I'll take the average of f and g. That would be f of x plus g of x all over 2. Because that's the average of f and g. If you take the average, that will bring you to the middle of the strip. Okay. Another way of, I guess that's the way of looking at it. You take the average of f and g. So that would be f plus g all over 2. And probably if you're good at memorizing, probably you see this in some calculus cheat sheets that the y bar is given by f of x squared minus g of x squared all over 2 dx all over the area. Well, the 2 here is just the 1/2 from the formula over there. And then you simply multiply f plus g by f minus g. You get f squared minus g squared. All right. Okay. So just remember this formula. So probably I suggest the first step is to find the area of the region, or at least set up the integral that will give you the area of the region that goes in the denominator of both x bar and y bar. And the next is to set up the numerators. Either use this for x bar, and use either this or this for y bar. Okay. By the way, the numerators for x bar and y bar are called the moments with respect to y and with respect to x respectively. But I won't get too technical about it. So you can just look at them as a weighted sum of the x values. Okay. Let's see some examples to see these formulas in action. And you know what? I'm a person who dislikes memorization. So that's why I usually want to attach formulas with concepts and understand why these formulas came about, so that I understand why the formula looks like that, so I can recreate them on the fly. But if you're good at memorization, then good for you. You can simply memorize those 2 formulas there. Okay. Okay, let's try an example. Perhaps let's do problem 36 from worksheet 4. Here we have the region R bounded by, oh, go ahead, Robert, question?
Oh, I accidentally hit it because I was trying to close chat.
Okay, no problem, yeah. Okay, so 36, y equals x squared plus 3x, x equals 0, x equals 3, and the x-axis. Yeah, I'll need to add the x-axis here. I guess the original problem 36 doesn't have the x-axis as a condition. So yeah, I'll just put the x-axis there as an additional boundary. Now let's sketch the region. Okay, so y equals x squared plus 3x is a parabola with vertex at x equals negative b over 2a. B is the coefficient of x, so that's 3. A is the coefficient of x squared, so that's negative 3 halves. So when x is negative 3 halves, I get y equals, I guess, negative 9 over 4. So you can do the calculations later, verify that those are the true values. When x is 0, y is 0. When x is 3, we get what? We get 9 plus 9, so that's going to be 18. Say 18 is over here. So the parabola will look like this, or at least a portion of the parabola will look like this. We're interested from x equals 0 until x equals 3, and we bound it by the x-axis. So basically, the shaded region will look like this. This is our region R, okay? And we want to find the centroid, okay? But again, for the centroid, we need the area first. Okay. The area of the region, I hope you still remember. Let's take advantage of the fact that this is an integral with respect to x. So here we have dx equals integral from 0 to 3, because the region started at x equals 0 and ended up when x is equal to 3. And then it's the area of a region. We're using vertical strips. So this will just be top minus bottom, right? It's going to be x squared plus 3x minus 0. And that would be the area. I guess if you carry out the integration, you get 45 over 2. I hope that's correct. Kindly verify that. So that's the area. So for x bar and y bar, there would be a 45 over 2 in the denominator. Okay. Now the centroid is at x bar, y bar. Oops. Where x bar is equal to, remember it goes with the area in the denominator. So let's put 45 over 2 there. Then integral from 0 to 3 dx. Remember, it would be weighted by the length of the vertical strip. So the length of the vertical strip is x squared plus 3x minus 0. You can drop the minus 0 if you want to make it neater. And then remember, we are taking the sum of x's, so there would be an x over there. Because I can plug in x there because I'm integrating with respect to x. And then I'll leave the integration to you guys. That would be easy because you only have here a polynomial. You need to integrate x cubed plus 3x squared from 0 to 3. Now let's look at y bar. Y bar also has the area in the denominator, so over 45 over 2. Still the integral from 0 to 3, oops, of the weight, which is f of x, top minus bottom. But remember, we are getting the central y value. So I am supposed to put y inside the integral, but that won't fly because I'm integrating with respect to x. So instead of y, I will put the average y value, right? But again, the average y value is the average between the top and the bottom function. The top function is x squared plus 3x, plus the bottom function is 0 all over 2. And then you can simplify this as 2 over 45 times 1/2 integral from 0 to 3 of x squared plus 3x quantity squared dx. Or if you want, if you're using the second formula that I wrote earlier, this will look like this. And that's what you want to evaluate. Okay. And then you get a value for that integral. Okay. So I leave the integration to you guys to find the value of x bar and y bar. And we will need that x bar and y bar in order to find the volume of the solid using Pappus's theorem, which we will do on Friday. Okay. Any clarificatory questions? All right. Perhaps when you try your quizzes and homeworks with surface areas, arc lengths, centroids involved, maybe you will have more questions. So I hope on Friday you go back with some questions on this topic, and then I'll try to come to look at some examples for exponential growth and decay plus what else? Separable differential equations. All right. Okay, so if there are no questions, then let's call it a day. Thanks for coming and see you again on Friday, guys. Enjoy the rest of the day. Yep, you're all welcome. Bye.